added it. It's dirty, I will write it back to disk. Whether it's committed or not is irrelevant because that's the whole point of still and no force. Do you follow me? So at the time of crash, what do you need to do? You need to make sure you undo all the changes, whether it's in the buffer or have been reflected to disk already. What about these guys? Even if they have committed, but because you're using no force, the dirty pages of these transactions may or may not be reflected in the disk because you're using no force. In other words, at the time of commit, you do not force what? Those transaction dirty pages to be written back to disk. All you force at the time of commit is to make sure their log records are written back to disk, but not the dirty page themselves. But maybe buffer manager have since then, from here to there, has written back those dirty pages to disk. It's possible, but we don't know. Okay. Lastly, for the aborted transaction, what happens? Well, it may have completed the abort process and written bunch of CLR. But CLR is an update record, right? Meaning it's undo a particular action. So it's an update operation, which means CLR will cause some additional dirty pages in the buffer. But again, you are using still and no force, meaning there's no guarantee those dirty pages caused dirty by CLR have been pushed back to disk. So what's the point? The point is to ensure atomicity for those aborted transactions. When the system has crashed, when you come back on, you need to potentially redo CLR. Meaning, yes, you never undo CLR, but you may need to redo the undo. You never need to undo the undo, but you may need to redo the undo because it's an update operation, and because you are using still and no force. I hope all that discussion makes sense. Okay. Coming back. But even with all this said, okay, with Red Hat logging, fine. If system has crashed, naive solution is I will just roll back to the beginning of time. Forget about my database state. I go back to the beginning of the time. That's the first record in my database log. And I honestly carry out each log record one by one. By the end of the day, I can reconstruct the database all the way to the time the system has crashed. But that's obviously very expensive, right? That's why people introduce the point, the concept of checkpointing. The point of the concept of checkpoint is similar to the checkpoint in going through airport security, right? You have level 1, you have one line of checkpoint, you have another line of checkpoint. The point is, after you go through one checkpoint, you never have to go back to that. You backtrack to the latest checkpoint you have passed. So that's essentially the idea of checkpoint. And in particular in database, when I do checkpointing, what I do? I will basically take a snapshot of my transaction table and dirty page table and dump that to disk. In other words, all checkpointing is doing is to keep a copy of the transaction table and dirty page table at the time of checkpointing and dump them to disk. Why do you do that? Why do you do that? By the way, these take time, right? Take a snapshot of dirty page table and transaction table and write them back to disk. These take time. So when you start checkpointing, you write a log record called begin checkpoint. You make a snapshot copy of the transaction table and dirty page table. You write that snapshot copy of these two tables back to disk. Once you finish doing that, you write end checkpoint. In between begin checkpoint and end checkpoint, updates may continue to happen to either of these two tables. So at the end of end checkpoint, your transaction table and dirty page table may already be different from the tables you have written back to disk, which only reflect a snapshot of those two tables at the time of begin checkpoint. Okay? Alright. Now when system has crashed, what do you do? When system has crashed, you roll back to the last checkpoint. And that's essentially how do you know when is the last checkpoint? That's the master record. Okay, that's a master record. And you try to do what? You try to play the log forward, and what do? You try to reconstruct the content of your transaction table and dirty page table all the way to the point of crash by looking at your log. And then using the reconstructed dirty page table or transaction table, you perform redo and undo. That's what I'm going to do next. There's a one subtle observation here though, which is start from the last checkpoint, you play the log forward, you try to reconstruct the dirty page table and transaction table, right? All the way to the point of crash. You may never be able to reconstruct, the content of those two tables all the way to the last minute right before crash. Why is that? The reason is these guys are gone forever. So you can only reconstruct the transaction table and dirty page table all the way to the flash LSN before the crash. But these guys are gone forever, which means you may never know the exact content of the transaction table and dirty page table right at the point of crash. But that's okay. Why that's okay? I will come back to that point later. Now let's do the analysis phase. Let's first do the analysis phase, right? So you start from the last checkpoint. What do? You reconstruct the dirty page table and transaction table. The dirty page table has two things. One is page ID and record ISIN. The first record ISIN causing the page to be dirty. Transaction table has what? Transaction ID, status, running, committing, aborting, last milestone from that transaction. So you load these two tables from disk at the point of checkpoint, you play the log forward. What you do is, when you see an end record, what do? You remove that corresponding entry from the transaction table. For all other records, you add the transaction ID to the transaction table if it's not there. If it's already there, you update the last LSN while you play the log forward. When you see a commit or abort log record, what do? You change the status to committing and aborting. Otherwise, it's running. That's what you do for transaction table. Okay. What about for dirty page table? What about the dirty page table? Whenever you see an update record, if you have an update on a particular page and that page ID is not in dirty page table, you add that page to the dirty page table and set the record ISIN equal to that log record, log sequence number. Because this is the first log record causing this page to be dirty. Okay, then you're done. One subtle thing, here's another subtle point I'll try to make. The dirty page table might not reflect, even if you have done this, even if we ignore those log records that's not been flushed to disk, even if we ignore that, the dirty page table may still not reflect the exact content of your dirty page table at the time of crash. Why? Because we don't know what the behaviors are for the buffer table. We don't know the behavior of the buffer table. Right before the crash, the buffer manager might have written some of this dirty page back to disk so that they are no longer dirty. But we simply do not know that. We never log the behavior, we never log the action of the buffer manager. However, if you think about what we're doing, we maintain essentially a superset of dirty pages in the dirty page table than what the true dirty page table may look like. Maintaining a superset here is okay because all you want to make sure is I take care of all the dirty pages. So having a superset is okay. It has a negative impact on your efficiency, but guarantees correctness at the end of the day. So that's why it's okay. Okay? So that's another subtle point I should make. Now the redo phase. What about redo? Now once we have the dirty page table and the transaction table in place, we can perform redo. The point is, where do you start redo? Well, you look at your dirty page table. You may have 5 or 10 or hundreds of different dirty pages. One of them must have the smallest record ISN value. And that's where you start redo, because that's the very first record causing any of your page to be dirty. That's where you want to start redo. Does that make sense? The naive solution is to simply redo everything from there all the way down. But that's very inefficient. Of course, that's a correct solution. You basically start from there. Whenever you see you redo two types of things. You redo update log record and you redo CLR for the read and extend. So you basically redo everything in between. But that's very expensive. You can do some optimization. What are some optimization you can do? These are the things you can do. First of all, if you have an update log record affecting a page that's not in your dirty page table, do you need to redo that? The answer is no, you don't have to redo it. Why you don't have to redo it? The fact that it is not in dirty page table means that, yes, it was caused dirty by this current update log record, but since then, the buffer manager had written it back to disk and removed that from the dirty page table. And the fact that I didn't see you in my dirty page table after analysis means that buffer manager had already written it back to disk before the last checkpoint process. That's why you are not in my dirty page table. That's why I don't have to redo this update operation. So I guarantee that this change has already been reflected on this, so I don't have to redo it. Affected page is in the dirty page table, but the record ISN is greater than the current log record you're looking at. Then you have to redo. This basically is the same idea. Yes, this current log record causing this page to be dirty, but since then it's been written back to disk. And then, so buffer manager remove that page from the dirty page table, but then another transaction come back and cause the page to be dirty one more time. That's why the record ISN for this dirty page is smaller than, is ahead of the current log record you're trying to redo. So you can skip this update log record. So it was a valid update operation causing the page to be dirty, but since then it's been written back to disk, and then the page becomes dirty again by a subsequent update operation. And this particular update must have been written back to disk. The fact that my record ISN for this page is greater than the current log record. The last one is tricky. The last one is the first two conditions fails. So you potentially have to redo. So you load the page from disk to main memory, you try to redo, right? You load the page from disk to memory and try to redo. But after you loading the page back to disk, you realize the page ISN on that page is greater than the current log record you are looking at, you are trying to redo. What that means is, this is the final piece of truth. The buffer manager indeed had written the update calling caused by this log record back to disk. And that's why page ISN is greater than ISN. Page ISN denotes the last update operation applied to a particular page. The fact that the disk version of this page has a page ISN greater than or equal to the current log record means that buffer manager must have written this change back to disk. But you don't know this until you have load the page back to main memory. But at least you save an I/O of writing it back. You have to spend the I/O to read it back to memory, but you skip I/O of writing it back. So those are the three optimization potentially you can do. You don't log redo. Why you do not log redo? Why you have to log undo and you don't have to log redo? Because you can always redo the redo by just looking at the original log. But you can never remember you have undo something if you don't log it, if you don't do logging work. The undo phase is very similar to the abort process I have described. The big picture is this. You start from here, you go back. And you start from the transaction table. You find out the max LSN. Whatever in the transaction table are the ones you need to undo. Right? Because otherwise, it's either it's AND. It's AND means that you don't have to worry about undo. So you start with the largest LSN, and you go backwards. And the only tricky thing here is you continue logging while you undo by writing a CLR record. And why we need CLR? If you think about it, essentially, system may crash during the process of undo or redo. When you come back on, you need to figure out whether you have undone something or not in the previous crash recovery phase. This is very similar to a movie called Inception, right? There are levels of dreams. Right? You need to figure out whether you are in a dream or not. If you are, you need to figure out which level of dream you are in. The CLR basically facilitates that to keep you, to remind you whether you have undone this or not in a previous crash recovery attempt. Okay? With that, I think we covered everything. Unfortunately, I do not have time to go through these examples. I will leave that for you to look at this example yourself. And coming back from the Thanksgiving holiday, I will spend some more time to go over this. But you have everything you need to know to solve problem 4, homework 4. I will also release lab 5 today. Okay? All right, thank you. Have a nice holiday.